Ter usar tempo de ir acompanhando, assim?
É essa a ideia.
Essa é a ideia.
Okay. Now we will start the next presentation. It will be a hands-on on QEMU about prototyping RISC-V extensions. My name is Matheus Ferres. I work at Eldorado in the embedded computing department. I have a master's degree in electrical engineering at Technological University of Paraná. And I've been working with QEMU for a few years. We've worked for the implementation of the Power ISA 3.1, and we also gave maintenance to the PowerPC targets of QEMU for a few years. Here's our agenda for today. So I believe that most of the audience is familiar with RISC-V, but here's a short introduction. RISC-V is a small ISA, a small base ISA with a bunch of extensions. It was built with the idea of extensibility. So, for instance, you have the multiplication instructions that is not part of the base ISA. You have the atomic instructions that is separate in another extension set. And you have the vector ISA that is also separate. And RISC-V reserves some opcodes for extensions that is not made by RISC-V International. So you have custom 0, custom 2, custom 3, and custom 1. Those opcodes can be used, and we have the guarantee that in the future RISC-V will not use those opcodes. So it's an ISA that is friendly to be extensible. And when you are developing an extension, you will need some kind of simulation. And today we will present QEMU as a simulator. So QEMU is a generic machine simulator and virtualizer. It serves both to simulate a machine and to run virtual machines accelerated by hardware. You have the system mode that is also called soft MMU. It's where you have the entire machine virtualized. So you have the CPU, the memory, the devices, the bus, everything is emulated. And in this mode, you can use something like KVM to accelerate the execution of this VM. You also have the user mode. That's what we use today. In this mode, you will be running a user space program using QEMU. It's much faster because you don't have to emulate, for instance, memory access. And the only job that QEMU is doing with this kind of emulation is to translate the guest instructions to host instructions, translate syscalls between the guest kernel and host kernel, translate POSIX signals, generates syntactic signals when the emulated code does something like illegal division or executes an illegal instruction. And in this mode, it does not have hypervisor support. So why use QEMU? Well, first, because it's faster than other simulators. If you have the RTL for your design, you can use something like Verilator, but it's very slow.
That's why it's called there.
Yeah. Sorry? The other option is Gen 5, that is faster than Verilator, but it's quite slow. QEMU can be used in user mode to test your compiler or to test libraries. And then you can go to system mode to test bare metal code, to test the Linux kernel, to test if context switching is correct, if the traps are being generated for your user space process, to test the interaction between applications and devices. QEMU also has a built-in tracing and logs that also have very good performance. There is an integrated GDB server where you can use breakpoints, watchpoints, sync set to the code, and use Python scripting to automate testing. There's also semi-hosting support. Semi-hosting is a standard developed by ARM to test devices, and it was released under the Creative Commons Zero license. So RISC-V adopted this license, and it's now ratified, and QEMU supports that. And you also have a thing called TCG plugins that can be used to analyze the workloads. So you can develop a very fast simulation and add the instrumentation for your code as a plugin. So you only pay for the instrumentation when you actually need the data, while you are iterating, developing software, trying to make your library do the right thing. You don't need to pay for the instrumentation cost. So for the courage ones, for those that will be following along, that's a tentative list of what you need to install to build QEMU. I'll give you guys a few minutes if you need to type key commands. All good? Okay. All right. And then you can clone the QEMU repository, configure the target, and start the build. and move on.
Are you going to use all these targets?
The main target is the RISC-V user mode, 64-bit. However, I always recommend to build for at least a 32 and a 64-bit and a Linux user and a software emulator target, because it's very easy to write code that builds for one target and not the other. So even if you're not using it right now, build the 4 targets. The overhead in the build is negligible.
I see.
So it's probably worth the extra time.
Still downloading stuff here, but I think we can advance.
Okay.
Let's multiple commands.
So, about QEMU internals. When QEMU is emulating, it will use an accelerator called TCG, the time code generator. It's used both in system emulation and user mode, and it's the only accelerator that allows cross-architecture emulation. So you can have an x86 machine and run a RISC-V processor. It was meant to be a C compiler backend. However, it was simplified to work inside of QEMU. The parsing part of the language was removed, and instead you have the parsing done by the target architecture. So, for instance, you have the RISC-V parser that will decompile the RISC-V instructions, generate the TCG intermediate representation, and then the TCG backend will compile this intermediate representation back to instructions that your processor can execute. So here's a simple image, like a 8,000 feet view of the process. You have the QEMU process that will load an ELF file, and you have 2 main loops, the CPU loop and the translator loop. In the beginning, the translator loop will look at the instruction pointer that the emulated processor is trying to execute, and we check if there is a translation block for this instruction. If this instruction is already translated, it will jump to the translated code that you execute until you have a jump. So it works as basic blocks, just like any other compiler. When you have a jump, you will go back to the beginning of this loop, or if you have an interrupt, like a device driver trying to deliver some data, or if the code generates an exception, like accessing an illegal address, it will jump to the interrupt runner that will resume the execution going back to the start of the CPU loop. If the current instruction is not translated, the CPU loop will call the translator loop, where you have the front end that will decode the instructions, emit the intermediate representation, and compile the instructions for the host architecture. This translation will be cached, so the next time that the CPU executes the same instruction, the code is already done, and you don't need to execute the translation again. It is a very simple, very primitive way of just-in-time compilation. You are decompiling and recompiling instructions during the execution, and when this translation block cache grows, older blocks will be evicted. So if you are not running a code for too long, it will be freed, and then if it's needed, it will run again. It will be translated again. So a bit more about the intermediate representation. So you have basic blocks, that is a sequence of operations that end in a jump instruction. You have variables that are strongly typed. They could be 32 or 64 bits. A variable can be a temporary that will live inside a basic block. It can be a local temporary that lives inside the translation block. Or it could be a global, like a CPU register, that can live across the translation blocks. And you have two aliases types, the pointer type and the target long type, that will be either i32 or integer 64 depending on the target. So RISC-V 64, both of them will be i64. Here's an example of some of the TCG operations. It is a RISC-like architecture that contains more than 190 instructions right now. So we have like the conditionals, unconditional brands, conditional brands, loads and stores, you have byte swap, you have move conditional, you have multiplication, you have logical operations, and here in this header is where the methods that generate those operations are defined. One operation, that is the call, is used to call helpers, so the just-in-time generated code can jump out of the translation block to execute a method written in C. So if you have an operation that is too complex to generate at runtime, it's better to write this operation in C and have the just-in-time code call your helper during the execution. You can optimize those helpers if they don't generate side effects or if they don't read logos. And TCG will do some optimizations when the call to this helper is being made. So the call is cheaper if you have those flags. So, how is your building going?
That's progressing.
Okay.
It's almost 400 targets already built.
Ready? Finished? We will run a first example. If you want to copy this very complex hello world and build that, and tell me when you are done. Can you build?
Almost there. 2,200 targets. 700 more.
And we're done. Run.
But the C code already built.
do acompanhamento do algoritmo. Aí você vai fazer o seguinte, vamos botar de novo, botar de tapado, não faço você faz mais ok? Ok. you finished? Good? Okay. Can you run the example?
No, the loader was not found. That's probably because I'm on another directory. Do I have a lib somewhere?
Yeah. So, what's the problem here?
Yeah, that's exactly it. LD.
Hello is dynamic linker,
Yeah,
and you need the dynamic linker to resolve the libraries.
right.
However, QEMU will look the standard dynamic linker def, that is inside of /lib/ld something.so. But we are cross-compiling, so our dynamic linker for RISC-V is in a non-standard path. To resolve that, you can pass the -L, capital L option, and to find the dynamic linker, you can copy the name of the .so file and look starting from your root. And you should find the file. The option that you pass to L is the directory that contains the lib directory, not the lib directory itself.
It's like the root prefix.
Yes. It's not a complete sysroot, not complete rootfs, but it's the bare minimum that the ld.so needs to load the libraries. If you don't want to pass the option all the time, you can use this environment variable. You can set it to this path and it will work the same. Or the option that we'll be using today, you can link the hello executable statically. It will be a bigger executable, you pass the static flag, but then you don't need the L flag nor the environment variable, and you can pass this executable around, and it will work mostly the same. All right. And now, a bit more of QEMU internals. So, the translation loop started with decoding instructions, and decoding is a very error-prone operation. Doing that by hand is quite tedious. So, the QEMU maintainers developed a Python script called decode tree. There is a generic way of decoding instructions of many architectures. Those are the architectures currently using decode tree. Some architectures like RISC-V have all the instructions implemented with decode tree. Some architectures like PowerPC have an older legacy written by hand decoder, and then new instructions are using decode tree. ARM is similar, and some architectures that is not shown here, like x86, are not using decode tree at all. That's for legacy architectures, you don't need that. So there's this decode tree.py file that is executed during the build of QEMU, and the output of this Python file is a bunch of C files that will decode instruction. It will have structs for each argument format, and it will have a method that you call passing the instruction, the integer representing the instruction, the opcode, and it will return true if the decoding was successful. And this method will call another method called trans_instruction name, and that's the method that you will implement to emit the intermediate representation. So you will write the instruction pattern that will be consumed by the decode tree, and you write this method, and that's enough to have a simple instruction implemented in QEMU. So about the decode tree file, you have the file is processed line by line. You have field definitions. Those field definitions have a range of bits. Here, for instance, it's the RS1, RS3, RS2 fields of RISC-V instructions. So it starts at bit 27 and it goes for 5 bits, so 37, 36, 25, and so on. That's a 5-bit integer that will be parsed by the code tree. You have argument sets that you will say what are the name of the fields of your opcode. You have a format definition where you can have some fixed bits, or you can have dots or dashes. Dots are the bits that will be parsed by a field. Dashes are bits that are ignored, and ones and zeros are the masked bits that will be compared to identify the instruction. And then finally you have the instruction pattern. So here's an example, fmv.x.w. That's the fixed bits. That's one register, that's the field for another register. It's an R2 format. So during the execution, QEMU will call the decode function that will compare to this mask. And if it's a match, it will extract these two RS1 and RD fields, put in an struct, and call trans_fmv_x_w. And that's where the implementation of the instruction, the code that emits the intermediate representation, will be written. The syntax is a bit more complex. You have some transformations that you can do with the bits that you read from those fields. Here's the documentation if you want to read more. Let's learn it by doing. So here's our first instruction. It's not something useful, it's just a silly instruction to show us an example. We will increment a general purpose register until it's 10. If it's 10, you'll just copy from the input register to the output register. The major code will be the custom 0, that is reserved for custom instructions. The higher bits, the func 7, will be this pattern. The bits between the two registers will be 0, 0, 0. And for now, we want to use the RS2. So we start by writing the test. It's usually a good idea to test things, see if they are broken before you try to fix them. So first we will write a RISC-V program that will execute the instruction. We'll have an illegal instruction trap, and then we will start implementing the instruction itself. The compiler does not know about this instruction, we just made it for this presentation. So we will use a series of macros to emit the assembly using the .long directive and a fixed number, and that will be understood by the assembler that will generate the instruction that QEMU will try to execute. So start a new file, a new C file, put these macros there. I'll give you a minute. All good? Good? Not yet?
How many zeros? 6.
You can make the same number by making the instruction pattern and turning everything to
X.
yeah,
Yeah, of course.
plus to 0. It will be 1, 2, 3, 4, 5, 6 zeros. A, 6 zeros, and B. Alright. And that's how you use that. So to emit this instruction, we're using line assembly. Line assembly is a very complicated topic. It's very easy to shoot yourself in the foot, but it's the only way for now. So until you build your compiler or add this instruction to your compiler, maybe a talk for next year. That's the way we're using. Since this macro is doing arithmetic, you need to pass the number of the register. You cannot use nice names like T1 and T0. So you have to convert to like 5 and 6, but also a bit inconvenient. But there are other ways around it. But to be short today, we'll just keep doing that. Right. So do that with the static flag, just like the second hello executable, and try to run it. You'll be met with an error, which is the expected since the instruction is not implemented yet.
I was going to ask this. I mean, where have you defined the instruction? It hasn't been yet, right? So
Start with the test.
I leave
See it's broken and then
that makes sense. Yeah.
test-driven development
Yeah.
hard. That's how it should be.
so now let's use. You need more time, Alfredo?
Yeah, I have a typo somewhere. It's just,
You have to check the
yeah,
file.
Funny enough, my client he was complaining about the T0 register name.
Oh,
I know, but it compiled. Yeah, it's just the language server. It's not a problem.
T0 should be known, but it's the base.
It's probably interpreting as a host. It's not a cross compiler aware language server. I think.
Could you please go back to the macro slide?
The /n/t should be in the same line.
Yeah. So, now, since I mentioned that QEMU has a built-in GDB server, let's use that. So, start with SG1234. If you want to run the same terminal, you can use that, otherwise you can run different terminals. And then start GDB with the same executable and use target remote 1234, and it will connect to the QEMU GDB server. Maybe you need to install the package. Sometimes it's separate from the other packages.
Yeah.
I couldn't fit on the first slide because it was already too crowded to put more dependencies there.
This is probably GDB dash RISC-V instantly, right?
The same prefix of your GCC. First of GDB.
Package GDB RISC-V GNU available, but it's referred to dynamic package.
There's another package. It's a Debian system.
Yeah, it's Ubuntu.
Yeah, there's another package called GDB-multiarc. Can work with.
GDB saying that it's not in our architecture.
Sure.
Yeah.
That makes sense. It's just the other package not stable. I had some hope. Anyway, let's move on.
The width in GDB chart is just GDB. Is there
This is GDB multiarc.
You work for a company, but now you can fix that.
Yeah. maybe 2 more pointers give me, I might be able to push a package to the archive. I'd love to. Yeah, it's doing something.
Alright.
Could not connect. Oh, the other. Mhm. Good. Let's start. Continue.
After the target remote, you can give a continue command.
Mm-hmm.
Usually, when you are using GDB locally, you use run, but run will not work if you have a remote target, so it's just continue. And then it will receive the signal because you had a legal restriction. If you use the examine command to check the PC, PC is the program counter, so you are looking at the memory in the address pointed by PC. It will be this address and it will be this content. Here we have the A and the B, and there's 6 something here, but it was 0 before in the mask, but now it's a 3, a 2, and a 8. That's the register that were allocated by us, the 5 and the 6, with the correct shift and the OR with the mask. And if we continue, the program will be killed, but because the signal was not held. How good? That's what we expect. Now let's start the implementation of this instruction. So we'll go to this target RISC-V int32 decode file, go to the end of the file and add this line. It's the name of the instruction, the major code, the minor code. In the middle we have the ignore bits for RS2, dot for RS1, zeros for the tree, and dots for RD. And the format will be R2. Here's 5 dashes, 5 dots, and 5 dots.
So how do you plan to design the instructions to be included?
That's another problem in a different field. Usually you have to find repeatable things that your program do, and you have to assess if what is the cost of implementing that in software, with normal instructions that you already have, and the cost of implementing that in hardware. So for instance, this particular instruction is not very useful unless you had, for whatever reason, that's something that your program will do a lot. Like you are reading a sensor that you need to add one, and you want low latency for whatever reason. When you have the code pattern in your file, we'll make the translation method. So it will be trans underline the name of the instruction. The first argument is always this instruction, this is context. It is defined inside this the RISC-V folder, but we will not touch that for now. It's a big structure with everything that you will need for decoding. And the second argument is underscore R2 because it's the R2 format. The content of this R2 register, the R2 structure, will be defined by the R2 format, which is RS and RD. RS1 and RD. So about the implementation of the instruction itself, on the first line we will declare a TCG variable that will get the global register, RS1. So it's a general purpose register with the number defined by RS1. We have a second variable that will be a temporary. We will add 1 to this to the value of the register, and then we will use a move conditional to compare 0 with a constant 10. And if it's less than 10, we move the added value to T1. And if it's not, we will keep T0, that is the original value. Then we set the register again, and we return true to tell the decoder that we were successful at decoding this instruction.
TCG gen line, it's like spelling almost assembly, right?
Yes, it's in some sense it's worse than assembly. It's intermediate representation. So assembly you have a fixed set of registers, and here you have like the variables that don't live across jumps. So if we had a TCG gen BR, that's the unconditional branch, after this branch, every other instruction that access these variables would be illegal.
Mm-hmm.
So it's a bit harder than the writing assembly itself. That's why we have helpers, because if it's a very complex code, it's very hard to write the C code that generates an optimized operation. Around here.
All good so far.
So let's run the same program again, and hopefully you'll not see the bigger instruction. So run Ninja again to build QEMU.
Okay.
Of course, it's a compiled program, compiled language. Okay, 3 and 4, all good.
Failed. the code in C. Probably a type. Definition has 31 bits.
Yeah, it's missing.
Dash, a dot.
It's 5 dashes, 5 dots, 5 dots.
Yeah.
The first field is 7 bits. No, 6 bits.
6. Here we have 7.
It's 7 bits.
5 dashes, 5 dots, 3 zeros, 5 dots. 7 bits again.
It's missing.
1 0, yeah. Yeah.
Now let's make things a bit more interesting. Let's edit the test program to have a loop around the assembly block. So the instruction is executed 10 times.
Still got any instruction. Still? Oh, it failed to compile. That's probably another. Let's see.
If you run the new program, compile it again, same command as before. If you run, you have the value being incremented until it's 9, then it's 10, and it will not go beyond 10.
Can you go back to the for loop, please? Yeah, it's right before the assembly.
Before here, and copy in and out after the printf. Okay. Is that the output? Up to you.
You can see the last line. Go back to it. So, yeah, close out. I see.
Can you go back to the translation definition?
This one?
2101 on T constant 10 T1 oh T1 swap that. Structure was
Different.
Thank you.
So now, just to check if we understood everything correctly, let's use GDB on QEMU itself, and let's put a breakpoint at the translation method that we just developed. Then run QEMU and tell me how many times will this breakpoint stop the program. Any guesses before we run? 0 times, 1 time, 10 times? Instructions inside the loop. Installation is only once. Good?
I'll bet it's 10 times.
10 times?
Yeah, let's be negative. Optimistic.
Okay. Just once? Yep, just once. So if you want to check, you can continue, and at the end you can use info p to show how many times the breakpoint was hit. And it was a single time. Why it's a single time? Even if the instruction is being executed many times, the instruction is inside this basic block that will be translated a single time, and the basic block will be executed 10 times. But the translation process will happen once. Because again, QEMU is just in time compiling, decompiling, and recompiling your program. Alright, now comes the funny part. So we'll make a new extension, now a bit more useful one. Right now, RISC-V International as a SIG vector with 3 test groups discussing matrix acceleration. We have 3 approaches so far. We have the attached matrix extension that we add new input and output register for matrix multiplication. It's something like ARM did with SME. We have the integrated matrix extension that proposes that you don't need new register, you just use the vector registers to hold the matrices and avoid adding new architecture state. And you have the vector matrix extension that is new. This test group started this month. And the idea is that vector registers can be the input, and a new kind of register can be the output, and you have other products of the vectors. And then you have one or more accumulators that we decided to implement. We'll make our own VME-like extension. We'll do whatever we want because it's just simulation. We are not bound by the physical means of silicon. So we have 32 very big accumulators. We have instructions to load and store this accumulator for the sake of context switching, for instance. No widening or narrowing of the data types to keep the function simple for this talk. We'll have a floating point and an integer operation. And in total we have 4 instructions. A vector load to load the accumulator, a store for the accumulator, the integer order product, and the float order product. So, for the accumulator load store, we use the same opcode, custom 0, so the 7 lower bits of the instruction are the same. We use 110 or as the func3 option field, and we use this func6 for the load and this other one for the store. For the vector outer product operations, we have the same custom 0 measure code, this other func6 for each one. And let's start by writing the test again. So the same SRT and STR macros, and then one macro for each instruction. You can copy paste from the previous and just change the mask. The only difference that's the 2 arithmetic ones have a second RS2 argument, and then you just need to add the RS2 register here. Tell me when you are ready.
No.
Good. 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 So that's our test program. We have two vectors of each 32 numbers. And we have the accumulator, which is 4 by 4. And we have another variable to hold the result. So we load from this variable and store the result in a different one. Okay? Okay. Okay. That's the inline assembly, so we should make a main function and then put the inline assembly. So the first instruction is the one used to set the vector length and vector type. That's standard for RVV. We will set the size of the vector as 4 elements of the 32-bit type. Here we set tail agnostic and mask agnostic. For our use case, it doesn't matter. Then we move the address of the accumulator to register T0. Then again we use 5, that is the integer representation of T0 on the macro. Then we use the load instruction to load the vector load instruction to load the first vector. Then we load the second vector, and then we use the accumulate. Then we use the move again to get the address of the second, the last variable, and then we use the store So put the value back in memory.
This goes in a main function, not in the test function. That we just wrote.
It can be the main or whatever, whatever you want. It can be this function, and then you count it for main.
Okay.
I wonder if there's a way to save you guys this presentation so you can copy paste it.
Would be faster, but less fun. What is VL be between T0 and V0 in the last line?
The VL,
Yeah.
it's the CSR of the RVV extension that defines the number of elements.
Okay.
So this instruction, we set I, VL, I, is set in the VL CSR. So we have to tell the compiler that we are overwriting the value. And it sets to this integer form. Can we move to the next one?
Spaces after that's moving space.
Building this program, you need to tell VCC that you have this JRV name. So you should press -n arc equals RD64. I think it's right. It's hard to just type out 15 to press the next option. Looks good. You guys have access to this address? 1042.01. Can you ping this address?
Two, 01. No.
Look. Yes, I will email you guys this presentation. That would be work more faster. Otherwise, we won't finish that today. We pause the screen sharing just for a quick. You have an email that I can send you the presentation?
Yep.
If you want to type here, feel free.
It's faster.
I thought so. I mean, one suggestion maybe for next time is maybe have a Git repo with all the files,
That's probably a good idea.
because the guys could just, I mean, they can look at the files, right, and try to understand what you're describing, but at least they don't have to type.
I should have sent this presentation before.
Yeah, that works as well.
So now that you guys have these slides, you can copy paste. There's a second instruction, second ask block to test the second instruction. And again, a second print. The only difference here is the type of the format you are printing and the end of the loop. This is a bigger matrix. And then we will start the implementation. If you want to build this code, you need to pass -marg equals rv64 gcv. But that will be in the next slide. To use that if you want to build right now.
So these instructions are not implemented in QEMU, but they are, they are generated by the compiler.
Yeah. These instructions are part of RVV and they are implemented. This new instruction, we define it ourselves. So the compiler, QEMU, does not know about it.
Okay, so you are going to have a same.
So we have this .long directive that will emit this mask or with the values. And that's the opcode that the compiler would generate if they knew about this.
I see.
Other instructions here are all part of RISC-V.
Right.
When you guys are ready, please let me know.
architecture? Enlarge?
Oh, it's, here.
RV64 GCV. Thank you. Inclusive declaration of system.
Is it right on the Zoom?
Yes.
Double M, double C.
So.
Yeah, that might be the copy from the PDF sometimes weird characters will fall out.
So there's
If you look at the that's it's not really smart application, but the document from PDF is also not a great solution.
the other alternative is hosting. It sounds good.
Você tem um arquivo pronto?
Tem.
Mais fácil.
Let me do. So guys wants to copy the code, push it to my GitLab repository. So gitlab.com/mkfirst/QEMU. There's a branch called FOSForums. Here I have the complete implementation. Make it bigger.
And Diego hardware's turn, finally.
Okay. If you want to run this repository or just access this to copy the code from files, that will be faster. Right, can we move on? I'll just go over the next few slides because we're out of time. The basic idea to implement these circuits is first we need the architecture state. So this extension will add the accumulator, so we have to declare the accumulator. QEMU calls this the architecture structure that holds the architecture state, CPU arc state. The same structure will be type def to CPU RISC-V state somewhere else. So here in CPU.h, we'll call CPU arc state, but elsewhere in the code, we have the same structure with this different node name, with RISC-V name. What we need to do here is to add the accumulator. We have 32 accumulators that are VLAN by VLAN. So here's the definition that we use, and it should be aligned by 16 bits. Then again, you can go to the repository to copy this code if you need. It's just this line that you have to add. Then we need the code tree for the for instructions. So here's the definition, and then we add the helpers. Helpers need to be declared somewhere. So for RISC-V, it's helper.th inside the RISC-V target folder. The load helpers will use 3 arguments. So they return nothing. They receive a pointer, that is the accumulator that is being loaded. They receive an address, that is a target long for the architecture. And they will receive the env variable that will point to the CPU arc that we just saw here. The second and the third helper will have another argument. They will have one argument for the accumulator, one for the first vector, and one for the second vector. And again, the env value. We need some macros to calculate the offset inside the accumulator structure. Here's the tricky part. So our accumulator is just a big vector of Win64. That's all the vector registers are done to. So we use these macros to calculate where inside this vector a particular accumulator starts and a particular row of the accumulator or column of the accumulator. So here is the lm_addr macro that will calculate the offset inside a particular pointer. And then we have these other macros that help us by converting to the correct pointer type. Then we have the implementation of the helper itself. We have this macro helper that we use to declare the helpers. So here we declared VMLE32. Here we use helper VMLE32. What this macro does, basically, it's to call helper, and it's to rename this method to helper underscore the name of the instruction. So here we receive the pointer to the accumulator, the base address where we start the load, and the CPU RISC-V state pointer. We get the vector length, we get the elements, and then we go with a double loop for each element of the accumulator. We will calculate the base address plus some offset using I and j. Then we use this method to load the data from the guest memory into this temporary variable. And then we get the pointer to the element, and then we put the value inside the memory pointed by design. The store instruction is very similar, just instead of using the CPU LDL, we use CPU STL to write to the guest memory. The multiply the outer product instruction, also we have a double loop. We are basically reading the pointer from the vector register plus the offset of A and B, and then we multiply them together, accumulating C and write back. And then for floating point, QEMU has a library for soft floating point. So different architectures have different behaviors, different rolling modes, so you cannot directly use your guest floating points to emulate the correct behavior. So this instruction will do floating point 32-bit multiply add using the current configuration of the guest. So for instance, if the guest is configured to round to the nearest even or the nearest odd, that's what this operation will do. And as a bonus, if the guest current has the imprecise bit set, QEMU will use the hardware acceleration for floating point. So when the operation is not precise anymore, QEMU will optimize and do using the host instructions. Then we need the translator to call these helpers. So the first step is that we need a pointer to the accumulator. So we have inside the architecture state structure, we have one big accumulator array, but we need a pointer inside this array to the particular accumulator that we are loading. So here we get the offset of the ACC element of this structure, and then we multiply by the size of one accumulator. So the number of the register times the size of one accumulator. That's the offset inside the RISC-V, the CPU RISC-V state structure that we have to access. So at runtime, what we need to do is we create a temporary variable of the type pointer. We load the base address, and then we will add. We use the ACC offset to calculate from the CPU RISC-V state pointer plus the accumulator offset we will put in Destiny, and then that's the pointer that we will receive on your helper at runtime. Very similar to the store, and the only difference for the multiply accumulate instruction is that we have 3 pointers to calculate, one for the accumulator and 2 for the input vectors. Just like we have our ACC offset, the RVV implementation will have this VREG offset. It's the same idea, it will get the offset inside this structure to calculate the pointer that your helper will receive. Here's the compilation command. As we mentioned before, we need to tell the compiler that we have the V extension, otherwise it will not recognize the setVL or the vector load instructions, and then run the test. So I have this compiled here, so let's try to run it for you guys. So here's my fork of QEMU. That's the same code that I just put on GitLab. We should run QEMU here. I have the 2 examples in different files here, different than slide. But the idea is the same. So the first one is the integer one, so the 4x4 matrix. And the second one is the floating point, and that's the expected result. So guys, have any questions? I think we are out of time. Go.
How long took you to, in the real world, doing the work, how long took you to get this done?
I started yesterday.
No, maybe.
With the presentation, yes.
No.
It's really fast. The tricky part is to design the structures.
Yeah.
Implementing them on QEMU is not that hard.
Somehow,
How did you get to this point of understanding of QEMU? Like, how many years playing with it and why?
I was very, very lucky to have someone to pay me to study that. That was Eldorado, because we had a partner that financed our work on QEMU for PowerPC. And then we
That's
just...
IBM.
Yeah.
You can say the name.
Yeah, it was IBM. I don't want to say it was IBM, but yeah, it was IBM. It was this guy, particularly. So basically, we went there, we read through the code, and we were very fortunate to have QEMU has an amazing community, especially the guys from Linaro, like Christian Henderson or Peter Mendel. And they were very patient with my mistakes, and every mistake that I made, they corrected me, and that's how I got this understanding. And I'm here today teaching you what they teach me the best. So I hope you can also pass along this knowledge and use that for your work at home.
now we know where we are, so we can ask questions.
Yeah.
Okay, you can find me on LinkedIn.
We're going to share your cell phone number.
You can,
Your WhatsApp.
I have your email.
yeah, you have my email, and you can use my WhatsApp too. Yeah, I will share that.
Okay.
Thank
Okay.
you.
Good. Thank you.
All right.
Thank you.
Good one.
Você sabe que se você abrir